Figuring out what strategy that you're going to use. So we've done trees and we've done Venn diagrams. So now we're ready for question number 9. All right, so Katie's serving percentage is 0.815. If she serves 12 times in the next match, find the probability that she will make exactly 11 scores. All right, now. Exactly 11 scores. Now, what does that mean? We want her to, like, win 5 times and lose once, basically, right? Do we care which ones she wins or loses? No, we just want her to win 11 of the 12. So how about if we start with 12C11? That would pick 11 out of the 12 to win. Any 11 out of the 12 to win. Would you agree with that? Now, what's the probability that she gets a winner? 0.815. And we want 11 of those? What's the probability that she won't get a winner?
What is that?
0.185. And we want 1 of those, and that's the answer to the question. So this problem is exactly like number 4 and number 5. Because when you roll a die, you get a 4 or you don't get a 4. You win or you don't win. When you guess on your multiple choice test, you get it right or you get it wrong. When she serves, she gets a score or she doesn't. So these problems, do you see how this problem is exactly like those? It is exactly the same kind of problem. All right, and finally, there are 2 decks of cards on the table, and Peter draws a card from each pile. So here's a deck of cards, and here's a deck of cards. He takes 1 out of this one, and 1 out of this one. What's the probability that both are red? Now, you don't need to make this harder than it is. What's the probability? Here's deck 1. Here's deck 2. What's the probability that he'll get a red one out of this deck? Well, technically 26 out of 52, but that's just 1/2, isn't it? Isn't half the deck red? So half, and a red one out of this one is another half. So what's the probability they'll both be red? 1/4. Red and red, 1/4. Neither is red. Well, wait, if neither is red, what does that mean? They're both black. And doesn't both black look exactly like this?
Yeah.
So the probability they're both black is the same as both red, 1/4. Exactly 1 is red. All right, now we gotta be careful with this one. Because if exactly 1 is red, that means he could get a red one out of this deck and a black one out of this deck. Or couldn't he get a black one out of this one and a red one out of this one? All right, so what's red and black? What's that probability going to be? 1/2 times 1/2. What is black and red going to be? 1/2 times 1/2. Since it could be this option or this option, what am I going to do with those 2 numbers? Add them together. So the probability that he gets 1 red, exactly 1 red, is 1/2. 1 is black, and the other is a diamond. Okay, so 1 is black, so we're going to get a black one out of here and a diamond out of here. Okay, so what's the probability of the black? 1/2. And a diamond is 1/4 because 13 52s. So that is, what, 1/8? Am I done? Be careful. This is deck 1 and this is deck 2. So I got a black one out of this deck and a diamond out of the other deck. What else could have happened? Couldn't I have gotten diamond and black? So that probability is 1/8 also. And then what do I do with those two options? Add them together. Now, could you have just done this one times 2? Yeah, because doesn't it make sense? It's going to be the same, just in the other order, so I times it by 2. Neither is an ace. Neither is an ace. So what's the probability of not an ace?
48, 52.
No ace is, would you say 48 52s? That does reduce, but we won't mess around with it. And how about this one? No ace over here. 48 52s. And what am I going to do with those two numbers? Now be careful. It's no ace and no ace. Neither one is an ace. So what am I going to do with those numbers? Multiply them. And that's the probability that neither one is an ace. Both are aces.
452.
What's the probability of an ace? 452s and 452s. So that would be that I got both aces. Both aces. The first is a face card and the second is a 6. Now this time they're telling me exactly what has to happen. The first is a face card. So what's the probability of a face card? 1252s. And the second is a 6. 452s. And those are getting multiplied together. The first is the queen of spades. What's the probability of the queen of spades? 152. And the second is the 6 of diamonds. 152. So our quiz tomorrow will not be that long, but it will be problems from that pool. Alrighty? That's our quiz tomorrow. You will need a calculus. You will need a calculator. Alright, so now we're going to start 9-4. Our test will be over the entire chapter. So we already had a 9-1, 9-2 quiz, remember? We had that quiz. I turned them back, I think. Maybe not, did I? Oh, yeah, that's right. I turned it back. A lot of people weren't here. Okay. And then tomorrow we're having our 9-3 quiz. And then we're going to start, we're going to do 9-4, 9-5 and have a test. And then we'll review for the exam and be done. Sad day. Okay, sequences now. We're going to talk about sequences. There are 2 kinds of sequences we're going to discuss. So in your notes, you see the word arithmetic. When you say that word as a noun, it's arithmetic. But when we use it as an adjective, it's arithmetic. So we're going to look at arithmetic sequences and geometric sequences. There are billions of sequences and all different kinds. These are the 2 we're going to focus on. Okay, so what are some arithmetic sequences? Let me just list a couple. So one arithmetic sequence would be this set of numbers. I got to be careful here. Quit talking. And here would be another one. and then I'll give you a couple of geometric. These are just random examples. Here's a couple of geometric. All right. Can anybody figure out the difference between, these are arithmetic, these are geometric. What is the difference between them, Robbie?
The arithmetic, you're like adding a certain number, and the geometric, you're multiplying.
Bingo, that's it, bingo. Arithmetic, in an arithmetic sequence, you get from term to term by adding the same number. So in this sequence, what am I adding? So that's called my common difference. Common means it happens over and over again. The common difference is 3. 5 minus 2, 8 minus 5, 11 minus 8. That's the common difference. What's the common difference in this one? -4. You can add a positive number, a negative number, a fraction, a decimal, it doesn't matter. As long as you are adding the same number, you're arithmetic. Now, in this one, I clearly am not adding the same number. I am, as Robbie said, multiplying. What am I multiplying by here? 3. That is called the common ratio. 6 divided by 2, 18 divided by 6, 54 divided by 18. The common ratio is 3. What's my ratio here? It's not 2. If the ratio were 2, it'd go 10, 20, 40, 1/2. Your ratio can be positive, negative, whole number, fraction, anything. Since we can't divide sequences, we're not supposed to divide, we multiply by 1/2. Instead of dividing by 2, we multiply by 1/2. Our ratio is 1/2. Okay, now, those are some examples, so I did examples. One of the reasons that we particularly study arithmetic and geometric sequences is they're so easy to use formulas for, to build formulas for. So let's look at my sequence, this one, this first one, and let's see if we can come up with a formula for that. The notation we use is A sub, whatever this is, which term it is. So for this problem, A sub 1 is 2. That means the first term is 2. Now, how did I get the second term? The second term came from taking the 2 and adding 3 to it. And then how did I get the third term? I added another 3. So in other words, I added 2 3s. Well, what happened in the fourth term? Isn't it 2 plus 3 3s? So if you look at the pattern that's developing, the first term was 2 plus no 3s. The second term was 2 plus 1 3. And then 2 plus 2 3s, 2 plus 3 3s, 2 plus 4 3s, and so on. So what would the 52nd term be? 2 plus 51 3s. Because isn't the number of 3s 1 less than the term we're looking for? Did all of you notice what Katie noticed? So if you, for some reason, needed to know the 52nd number, that's how you would figure it out. Now, in general, if you are arithmetic, how are you going to find terms? This is how you would find the terms in that sequence. But what if we're doing it in this one? Or another arithmetic sequence? And let's back up. Where did this 2 come from? What was the significance of the 2? The starting number. So there it is, number 2 was the first number, right? Where did this 3 come from? That's the common difference. And then, Katie and a lot of you noticed that the number that you multiplied by the 3 was 1 less than this. So if that's an n, I'm going to be multiplying by what? Be careful. N minus 1, 1 less than n minus 1. So if you, that's our general formula right there. Okay, I think you ought to memorize that, but the other teachers don't. So you know what? I'll give it to you on a formula sheet. You don't need to memorize it. What you do need to know is what it's used for. This formula finds terms in arithmetic sequences. Okay? All right, so let's apply it to my second sequence right here. This was my sequence. Started with 8. Suppose I want the 100th term of that sequence. So this sequence in the box, I want the 100th term. What does my formula say that will be? 8 plus, what's my common difference? -4. And then n minus 1 would be 99. So I can type that in on my calculator. 8 minus 4 times 99, that would be -388. So if you kept going with this all the way out to the 100th term, it'd be -388. All right, can we do the same thing with geometric? Well, our first, I'm looking at this one right here. So our first term is 2. How did we get the second term?
No.
Multiply by 3?
Really? Were you on the?
How did we get the third term? Multiplied by another 3, which is 2 times 3 squared. And then the fourth term, 2 times 3 cubed. So if I wanted the 50th term, can you tell what that would be? What would the 50th term be? 2
times 3 to the 49.
So, Katie, can we get a general formula for that? This is what it would look like for that particular sequence. But in general, for a geometric sequence, what do we start with? Our first number, which is 2, but it didn't have to be, it could be anything. And then we, in our case, we multiplied by 3, which was our common ratio. And how many 3's did we have to multiply by? N minus 1. That's it. That's your geometric sequence formula. So if you want a number in a list, that is what you want. All right? Quick story. One of my very first years of teaching, in fact, you guys know Andrew Michaels in your class. When I had his mom in class, she walked in one day, she's really smart, very smart. She walked in and said, "Miss Ford, my dad and I were watching TV. And they said that if you put 1 checker on the first square of a checkerboard, 2 checkers on the next square, 4 on the next, 8 on the next, and so on. By the time you got to the last square of the checkerboard, you would have enough checkers to reach the nearest star." And she said, "This is wrong. The nearest star technically is the sun, and that's 93 million miles away. There is no way this is true." Well, let's figure it out. Is that sequence geometric? It is. There are 64 squares on the checkerboard, so if I wanted to know how many checkers were on the last square, I would find the 64th term of that sequence using this formula. So the 64th term is the first term times the ratio to the 63rd. I multiply by 2. So my ratio is 2. So I type that in on my calculator. There are something times 10 to the 18th, 10 to the 18th checkers on that square. So I'm going to divide it by 3, thinking maybe I can get 3 checkers per inch. Divide by 12, divide by 5,280. This is how many miles of checkers are on that last square. Isn't that amazing? Peter said, no way. Yeah, way. It's absolutely true. Geometric sequences, you're like crazy. All right, you're out of here. Have a great day. Quiz tomorrow. Right, I see you tomorrow.